Hello, I'm going to teach you today how to do the longest common subsequence problem, and I will follow up later with an implementation in the Go language. So first of all, this is the equation for longest common subsequence. You can see A and B here. This represents this list of, this is a string divided into a list. This is another string divided into a list where I and J, these are indices. So you could imagine if we're comparing indices, index 0 to 0, we can be comparing B to A. So that's what that portion of the equation is. So T, this represents the two-dimensional matrix here. And you can see that I've initialized for convenience, and you'll see later on the 2D matrix with an extra row of all zeros and an extra column of all zeros. So this is pretty important first step that I've missed in other examples online. So, so continuing on with this explanation of the equation here. So you can see if the strings are equal, then what we do is we look at the previous row and column and we add 1. So in this case, they're not equal, and then we take the max of either the previous row or the previous column. So you can see in both of these examples, it's 0 and 0. So the max of 0 and 0 is 0. So then we're on to B compared with B. So you can see that in this example, B and B, they are in fact equal. So we follow this path, looking at the previous row and column. It's 0 plus 1 is 1. Then we're comparing B to C. They're not equal, so we're on this else. And then we're going to take the max of 1 and 0. So it's 1. And then again, B and D, they are not equal. So we'll take the max of 1 and 0, which is 1. So on to the next row, we're comparing C to A. C to A is 0, max of 0 and 0 is 0. Next comparison is C to B. So C and B are not equal. Then we take the max of 0 and 1, which is 1. And then let's stop here to quickly see if this is like a does this make sense check. So you can see that we're comparing strings B and C with string A and B. So the longest possible common subsequence in this is just B. So this B is equal to 1, so that does make sense here. So then comparing C to C, you can see C and C are in fact equal. Then we follow this path. We'll look at the previous row and column is 1, and we'll add 1 to that. So our longest common subsequence now is 2. And then C and D, they're not equal. Max of 2 and 1 is 2. And then A and G, not equal. Max of 0 and 0 is 0. G and B are not equal. Max of 0 and 1 is 1. And then C and G, not equal. Max of 2 and 1 is 2. And then D and G, not equal. The max of 2 and 2 is 2. So then to return the strings, what we'll do is we'll compare 2. Where did this 2 come from? This 2 didn't come from here, didn't come from here, it came from here. So in any time you move in a diagonal direction, you'll return that character. So we'll return C. And then where did this 2 come from? It didn't come from the 1, it didn't come from this 1, it came from this 1. So then we will return this B. So our longest common subsequence is C and B. How to do the longest common subsequence in Go. This is pretty simple, but I'll walk you through it. First thing that we'll take a look at is this main loop. Main is initialized with we create a function called LCS, passing in 2 strings that we're comparing. So with the strings that we pass, we divide these up into slices of runes. So this is called A runes and B runes. Then we calculate the length of each, and we initialize a new empty matrix with an extra row and column of all zeros. And the reason we do that, when we remember, we step back in that equation to look at the previous row, previous column. When we do that, we don't want it to panic, so there will be a 0 there in that case. So this is the equation. So the equation will look a little bit different, but it's only because our reference has changed. So because we have the row and 0 initialized at 0, when we're making the comparison of our rune slices, you can see on this line, I and J. So these are our slices of runes, I and J. Then the place on the matrix in which we will add our operation will be +1 and +1, and then that means the previous row and column won't have the +1 and +1, so it would just be I and J, and then of course we add 1 for the previous row, previous column +1, setting it equal to the current row, current column. So in the max operation, I divided this up into two checks. So I've got this if else. So in this if else, we look at the previous row. So it's asking basically, so if the runes aren't equal, so suppose we've got A and B are not equal, it would look at the previous row. So it would look at in the two-dimensional matrix, the value on top, to see if that value is greater than the value to the left. So if the value on top is greater than the value to the left, then we'll set the current row, current column to the current row, previous column. And if not, the current row, current column will be the previous row, previous or current column. So that is just simplified, so I don't have to write a separate max function. So this goes through, it'll fill out the entire matrix, the two-dimensional matrix. And then of course I'll print it out. This is a little bit more complicated, so I'll have you do this mostly on your own, because it's kind of hard to talk through. But basically what this does is this will walk through our matrix in a reverse order, and anytime you look at the previous row, it simply decrements the X, and then every time you look at the previous column, it decrements the Y, so it steps up. And then we only make an append operation, so we return the answer or the matching character when we go in a diagonal direction, when we're stepping backwards through the matrix. So in this case, we'd walk through the matrix backwards, and it'll return B and C. And then this simply reverses the string. So we see this in the correct order. So let me jump out of here, and I will go run main go. And then you'll see a few of my print operations. So you can see this is the blank matrix. This is the filled in matrix. This is very similar to what we did on the whiteboard exercise. You can see that there are, in fact, two characters that are common, and then those characters are B and C. So our initial input, we'll go back to main, was B, C, and G, and then A, B, C, and D. And it's saying that the two in common are B and C. This again is our two-dimensional matrix, and to return the answer, it simply stepped backwards, and when it went in a diagonal fashion, then it returned their character. So that's it. I'm going to push this to GitHub. I hope you found this helpful. This was a little bit tricky, so the tricky part of this was basically conceptualizing this matrix. And really the hardest part that in solving this problem was initializing this matrix with a row of zeros and a column of zeros. this solved the problem of when I did this operation of looking back at the previous row, previous column right here, that it didn't panic. So there wasn't a panic. So that implies that the whole equation needed to be altered. So this will read a little bit different than what I took you through on the whiteboard, but the comments here that I'll push to GitHub will help you see that it's really exactly the same concept. We are operating on the current row, current column, and we're setting this to the previous row, previous column plus 1. So same exact equation concept, but it'll appear differently to accommodate the extra row and column. So the other tricky part in this basically was this backward stepping through the matrix to return the matching characters only on the diagonal movement, and then of course reversing the string. And that's it. I hope you found this helpful. Thank you very much. Goodbye.